This video is brought to you by mywayteaching.com.
Let us consider one more simple problem. A 3-meter long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall, as you can see in the figure. Find the reaction forces of the wall and the floor. This is the figure. S- So the ladder AB is of 3 meter. Okay. A is at a distance, its foot A is at a distance that is 1 meter from the wall. AC. AC is 1 meter. So AB is 3 meter. AC is 1 meter. See, from the Pythagoras theorem, we can calculate BC. AB square is equal to BC square plus AC square. We know the value of 2 and we can calculate the value of BC, that is equal to 2 root 2 meter. The forces on the ladder are its weight, obvious, isn't it? The forces on this ladder are its weight, W, acting at its center of gravity, that is D. So this force W. Reaction force F1 and F2 of the wall and the floor respectively. This reaction force F1 as well as F2. You can see here F1 and F2 of the wall as well as the floor. The reaction forces from the wall as well as the floor. Force F1 is perpendicular to the wall, isn't it? And since the wall is frictionless, force F2 is resolved into two components. Okay, wall is frictionless. This force F2 is can be resolved into two components. One is the normal reaction N, and one more is the force of friction F. Okay, this force F prevents the ladder from sliding away from the wall, and hence it is directed towards the wall. For translational equilibrium, taking the forces in vertical direction, for translational equilibrium, this N minus W must be equal to 0. And if you're taking the horizontal direction, then F minus F1 must be equal to 0. Isn't it? This is for translational equilibrium. For rotational equilibrium, taking the moments of force along about the point A, that is the arm 2 root 2, that is BC, isn't it? BC, and the force F1 minus 1 by 2 W. This point, the W and 1 by 2 about the point A and about the point C. So now we know W, they have given it as 20 G, where G is 9.8. We can convert it in terms of Newton. We will get it as 196 Newton. Okay. So the normal reaction N is 196 Newton. We can get this from this first equation. Okay. And from the third equation, that is this one, we can calculate the value of F1 as W by 4 root 2. We know the value of W, that is given by 196 divided by 4 root 2, which is equal to 34.6 Newton. isn't it? And from the second equation, we got the value of F1. So F1 and F are equal. So that is also equal to 34.6 Newton. So now we should calculate the value of F2, which is given by F square plus N square, because that is resolved into the components, isn't it? So we know the value of F and we know the value of N. That is 34.6 plus the value of N is given by 196 Newton. So F2 will be given by 199 Newton. Okay. The force F2 makes an angle alpha with the horizontal, and that tan alpha is equal to N by F. So we know the value of N and value of F. So alpha is given by tan inverse of 4 root 2, which is given by 80 degree. Okay, this is the simple problem. Now let us study moment of inertia. What is this moment of inertia? What is the analog of mass in rotational motion? In rotational motion, in the linear motion, we'll call it as mass. What about in rotational motion? What is the analog of that? Let us try to get an expression for the kinetic energy of a rotating body. Okay, let us try to get an expression for the kinetic energy of a rotating body. See, we know that for a body rotating about a fixed axis, each particle of the body moves in a circle with linear velocity, isn't it? For a particle at a distance from the axis, the linear velocity, that is Vi is equal to Ri into W. At that time, the kinetic energy of that particle is given by, we know this equation, that is half my Vi square, and we can also write it as half mi ri square w square, the kinetic energy of motion of this particle, where mi is mass of the particle. The total kinetic energy of the body is given by the sum of the kinetic energy of the individual particles. That one we can write it by taking the summation I is equal to 1 to n ki, that is equal to 1 by 2 sigma I is equal to 1 to n mi ri square w square. Here n is the number of particles in the body. Note w is same for all the particles, so we can take only w outside. So that will become 1 by 2 w square sigma I is equal to 1 to n mi ri square. So when we define a new parameter characterizing the rigid body called moment of inertia is given by, this is what we call it as moment of inertia. I is equal to 1 to n mi ri square. So with this we can write the kinetic energy as half I w square. Okay, the parameter I is independent of magnitude of the angular velocity. This is the characteristic of the rigid body and the axis about which it rotates. So, if you compare this equation of kinetic energy, what we got now, okay, of a rotating body with the expression for the kinetic energy of a body in linear motion, that is half mv square. Okay, then we get k is equal to 1 by 2 m w square, isn't it? So where m is the mass of the body and v is its velocity, we have already noted the analogy between angular velocity as well as linear velocity. V is equal to r into w, isn't it? So it is evident that the moment of inertia is the desired rotational analog of mass. So now we apply this definition of moment of inertia, which is given by I is equal to sigma uh, I is equal to 1 to n mi ri square, to calculate the moment of inertia in two simple cases. Okay. The first case is given by: consider a thin ring of radius r and mass m rotating in its own plane around its center with angular velocity w. Each mass element of the ring is at a distance r from the axis and it moves with a speed rw. Okay, you can see that in this figure. Each mass element of the ring is at a distance r, and the kinetic energy of this is given by k is equal to half m, mass is m, v square. We can also write it as half m r square w square, isn't it? So comparing this with the moment of inertia, we get I is equal to m r square. So this is a thin light rod of length 1 with a pair of masses rotating about an axis through the center of mass of the system and perpendicular to the rod. The total mass of the system is m. Okay, this is one case. And if you consider the second case, take a rigid massless rod of length L. So the first one is just the thing that we calculated the kinetic energy, and this rod is a second case where a light rod of length 1 with a pair of masses, we have considered a rigid massless rod of length L with a pair of small masses which are rotating about an axis through the center of mass which is perpendicular to the rod. So each mass m by 2 is at a distance of L by 2 from the axis. So the moment of inertia in this particular case is given by m by 2 mass L by 2 whole square, m by 2 L by 2 whole square. Okay, this is the second case. This table gives the moment of inertia of some regular shaped bodies about specific axis. You can consider a circular ring, the rod, the disc. So axis also given here, and even the moment of inertia. Disc, hollow cylinder, and solid sphere. Okay. As the mass of a body resists a change in its state of linear motion, it is measure of its inertia in linear motion. So whenever the mass of the body it resists the change in motion state of the linear motion, that is nothing but inertia in linear motion. Similarly, as the moment of inertia about a given axis of rotation resists a change in its rotational motion, we call that as rotational inertia of a body. It is the measure of the way in which different parts of the body are distributed at different distances from the axis. See, unlike the mass of the body, the moment of inertia is not a fixed quantity, but it depends on the orientation as well as position of the axis of rotation with respect to the body as a whole. So, here we define a new parameter that is called as radius of gyration. It is related to the moment of inertia as well as total mass of the body. So, just now we saw from the table that in all the cases we can write I is equal to mk square, the moment of inertia, where k has the dimension of length. For a rod about perpendicular axis at its midpoint, we can write k square is equal to L square by 12, isn't it? And we can write k is equal to L by root 12. Similarly, k is equal to r by 2 for the circular case. So, we consider different cases in that specific table. It is called the radius of gyration. The length k is a geometric property of the body and axis of rotation, and that is called as radius of gyration of a body about an axis. Okay. So, in other words, we can define this radius of gyration of a body about an axis as the distance from the axis of a mass point whose mass is equal to the mass of the whole body and whose moment of inertia is equal to the moment of inertia of the body about an axis. Okay. This property of this is extremely important quantity I, as a measure of rotational inertia of the body, has been put to a great practical use. Okay, in machines such as a steam engine, you can consider, and the automobile engine, they produce rotational motion and they have a disc with large moment of inertia, which is called as flywheel. Because of this large moment of inertia, the flywheel resists the sudden increase or decrease of the speed of the vehicle. It allows a gradual change in the speed of the vehicle. Okay. And this moment of inertia of a rigid body depends on mass of the body, shape, size, and distribution of mass about the axis of rotation. And even it depends on the position and orientation of the axis of rotation.